So what we did in this lab is we took a toilet paper roll and placed a beam right through the middle, and then we had the paper towel or paper hanging down. Then we hooked a mast to it, and we had it fall. And so it was spinning down, and this this portion here was causing the torque to go around. So let's go ahead and explore this situation here where we have a mass that's hanging down, and we want to figure out the acceleration of this mass that's hanging over this wheel and axle here. So if we draw our forces here, we have the tension going up, force of gravity going down. And so we can draw that out. We know you have that force of tension, and it's at a 90-degree angle here, right? It's 90-degree angle to the axis of rotation, so 90 degrees here. So the sum of the forces equals ma, and we've got that. We know that we have the negative force of tension plus the positive force of gravity equals ma. So that's the the linear acceleration. And if we solve for just simplify there, we've got that. Okay, now in terms of rotation, sum of the torques equals IA, which is the moment of inertia times the acceleration, angular acceleration. So we know that it's the force of tension causing this torque, making it go down. And so that's the force of tension times the radius, which we have the radius here, and then we have the tension here. It's 90-degree angle, so per amount of torque equals the moment of inertia times the angular acceleration. And so the linear acceleration is equal to the radius times the angular acceleration. And we can substitute that into the angular acceleration right here. So the linear divided by the radius, we place that into into here. And now we're going to have it in terms of linear, which is what we need. So we can multiply both sides by the radius, and we end up getting force of tension times the radius squared equals the moment of inertia times the linear acceleration. And the moment of inertia for a cylinder like this is 1/2 mr squared. We'll divide both sides by r squared. And so we end up with a force of tension equals 1/2 ma. And we can place that into the force of tension here. So we get the 1/2 ma. Now this is the cylindrical mass, and that's important to keep this separate. It's capital M. We have lowercase m for the hanging mass, and then again lowercase m for the hanging mass. And if we solve for the acceleration, we could bring both on this side. We can factor out acceleration, and we'll end up getting, this is our equation for the acceleration of the system. So what we had to do was we had to consider both the linear as well as the angular, and then bring those together. So with these values, we end up getting 3.09 meters per second squared. So now we have a fiber optic spool, and this spool is going to be pulled down by a mass, and here's the mass. Let's call her that lowercase m mass, and then we have the capital M mass for the whole spool, and which approximates a ring. So in this case here, we have a ring that is spun, and that mass is pulling down and going to spin the ring. And so you can see how it's hollow inside here, and that's why we're approximating a ring. And so yeah, so what I want you to do is go ahead and solve for the acceleration of the system. Let's call down positive, up negative again, because with the ring it's going to cause torque to spool it up, and we'll do that. So yeah, go ahead and pause the clip, and we're going to, you can derive the acceleration of the system using the sum of the forces as well as the torque involved. And when you're ready to check, you can hit play to continue. All right, so force of tension going up, force of gravity going down, negative force of tension plus positive force of gravity equals ma. And so we got the force of tension going down the sum of the torques equals I alpha, and force of tension times the radius, and we've got equals or times I alpha, and then again, remember alpha, we get into linear, which is linear acceleration over r, and then our radius cancels out. So the force of tension is going to be equal to the total mass of the ring times A, which we'll plug into force of tension here. And so again, capital M for that mass. So we place that in there. We have the negative sign, so negative capital MA plus mg equals ma. And then we solve for, we factor out A, and we solve for acceleration. So the acceleration of this system will be the mass that's hanging times g divided by mass, the small mass and the large mass. And so we can get the acceleration of the system. Okay, so let's consider this pool ball that we hit horizontally at a distance above the center of mass here. We know that if we hit straight in the middle of this, right, we're not going to cause any torque, just going to push this forward like this. But if we have a force that's above the center of mass here, we know we're going to get some sort of a torque there. And so we want to figure out, yeah, the D here, where the ball starts to roll, but it won't slip. So if we consider linear acceleration, again, sum of the forces equals ma. Angular, sum of the torques equals the moment of inertia times alpha, the angular acceleration. And we have the force applied here at equals ma, so that's the force that we have at the top. And then in terms of torque, we have the force over our lever arm D, and so that's the effective lever arm here, where this is a 90-degree angle. So we have the moment of inertia, which is 2/5 mr squared for a round cylindrical object like this. And we have alpha here as the angular acceleration. So linear equals angular times the radius. And we have we can rearrange again, the linear divided by the radius. We can place in here for alpha. So this is a constant theme that we're seeing here. The squared, r squared will be gone. The radius from the bottom will be gone there. So we're left with force applied times D equals 2/5 mRA. And we know that the force applied equals ma, which is the the mass times the linear acceleration there. And so we end up getting this here, we can divide both sides by ma, and we've got a bunch of things cancel out. So as long as the distance here is 2/5 of the radius, it turns out that it won't slip, because the torque here that's causing it to rotate will allow it to rotate, and the in terms of the linear, what's going on linearly, the object will accelerate, but again won't slip, where there's no